In this part, we study the losslessness property of microwave networks using impedance and admittance matrix representations. The objective is to establish the mathematical conditions that the impedance and admittance matrices must satisfy when a network absorbs no net real power. We will first consider a reciprocal lossless network and then extend the analysis to the more general case of a non-reciprocal lossless network. This distinction will lead to an important result concerning the structure of the impedance matrix. The discussion is organized in three main stages. First, we introduce the general important microwave network and recall the interpretation of incident and reflected waves at its ports. Second, we establish the conditions imposed by losslessness on the impedance and admittance matrices. Finally, two problems are considered to reinforce the results. The first concerns the admittance matrix of a lossless network, while the second examines whether a non-reciprocal lossless network necessarily has a pure imaginary impedance matrix. We begin with the general n-port microwave network described by its impedance matrix or equivalently its admittance matrix. At each port, the incident wave travels toward the network while the reflected wave travels away from it. The voltage and current variables at every port can therefore be related to the corresponding incoming and outgoing waves. For the present analysis, however, we will work primarily with the port voltages and currents. The wave representation provides the physical picture, while the matrix formulation allows us to derive precise conditions for losslessness. Consider first a reciprocal lossless n-port network. Reciprocity implies that the impedance matrix is symmetric, so the transpose of Z is equal to Z. Because the network is lossless, it cannot absorb any net real power. Therefore, the real part of the average complex power delivered to the network must be zero for every possible excitation. Expressing the average power in terms of the port voltages and currents, and then using the impedance relation V equals Z times I, allows us to examine separately the diagonal and off-diagonal elements of the impedance matrix. We first examine a diagonal element Z sub mm. To isolate this element, we excite only port M and set all other port currents equal to zero. The average power then depends only on Z sub mm and the magnitude squared of the current at port M. Since the network is lossless, the real part of this power must vanish. Because the current can be non-zero, the real part of Z sub mm must therefore be zero. Thus, every diagonal element of the impedance matrix is purely imaginary. We now consider an off-diagonal element Z sub mn with m different from n. We excite only two different ports, m and n, while setting all other currents to zero. The average power expression then contains the two cross terms involving Z sub mn and Z sub nm. Because the network is reciprocal, these two impedance parameters are equal. The resulting expression shows that the real part of Z sub mn must also vanish. Consequently, for a reciprocal lossless network, both the diagonal and off-diagonal elements have zero real parts. The entire impedance matrix is therefore purely imaginary. We now formulate the corresponding result for the admittance representation. The problem is to show that the admittance matrix of a lossless n-port network has purely imaginary elements. The proof follows the same general idea as the previous derivation, but this time we express the port currents in terms of the port voltages using I equals Y times V. We again impose the fundamental condition that the real part of the average power absorbed by the lossless network must be zero. Starting from the average power expression, we substitute the admittance relation between the current and voltage vectors. To determine a diagonal element Y sub mm, we set all port voltages to zero except the voltage at port M. The average power then depends only on Y sub mm. Since the network is lossless, its real part must be zero. Therefore, the diagonal elements of the admittance matrix are purely imaginary. We next consider two non-zero port voltages. V sub m and V sub n with m different from n. For a reciprocal network, the admittance matrix is symmetric, so y sub nm equals y sub mn. The cross terms in the average power expression can then be combined. Since the voltages can be independently selected, the condition of zero real power requires the real power of y sub mn to vanish. Therefore, for a reciprocal lossless network, every element of the admittance matrix is purely imaginary, just as we found for the impedance matrix. We now ask a more general and important question. Does a non-reciprocal lossless network always have a purely imaginary impedance matrix? The answer is no. The previous result relied on reciprocity. Without reciprocity, the impedance matrix is not necessarily symmetric, and therefore the off-diagonal elements need not have zero real parts individually. We now derive the general condition for a lossless network without assuming reciprocity. Consider an arbitrary n-port network described by V equals Z times I. For a lossless network, the real part of the complex power delivered to the network must be zero for every possible current vector. Using the Hermitian transpose, the average real power can be written as 1/4 of the current vector Hermitian transposed multiplied by the sum of Z and its Hermitian transpose, and then multiplied by the current vector. This form is particularly useful because it expresses the lossless condition directly as a quadratic form. Because the network is lossless, the real power must be zero for every possible current vector. Therefore, the quadratic form involving the matrix sum Z plus Z Hermitian must vanish for every possible current vector. The only matrix that satisfies this condition for all current vectors is the zero matrix. Hence, Z plus Z Hermitian must be equal to zero. This gives the fundamental condition for a lossless n-port network. The impedance matrix is skew Hermitian. The result can therefore be written compactly as Z Hermitian equals minus Z. This means that the impedance matrix of any lossless n-port network is skew Hermitian. This is the general losslessness condition in the impedance representation. Notice that we have not assumed reciprocity. Therefore, this result applies equally to reciprocal and non-reciprocal lossless networks. Let's examine what the skew Hermitian condition means for an individual matrix element. For a diagonal element Z sub mm, the condition becomes Z sub mm equal to minus its own complex conjugate. Writing the element as a real part plus j times an imaginary part, this relation requires the real part to be zero. Therefore, every diagonal element of a lossless network's impedance matrix is purely imaginary, even when the network is non-reciprocal. The situation is different for off-diagonal elements. The skew Hermitian condition relates to different elements. Z sub nm is equal to minus the complex conjugate of Z sub mn. This doesn't require each off-diagonal element to be purely imaginary. The real parts may be non-zero, provided that they satisfy the required skew Hermitian relationship. Therefore, a general lossless network has a skew Hermitian impedance matrix, but its impedance matrix is not necessarily purely imaginary element by element. We now recover the earlier results by adding reciprocity. For a reciprocal network, the impedance matrix is symmetric, so its transpose is equal to itself. Combining this symmetry condition with the skew Hermitian condition imposed by losslessness gives a stronger result. The impedance parameters must then satisfy the condition that each element is equal to minus its own complex conjugate. Consequently, every element has zero real part and is therefore purely imaginary. Thus, the important conclusion is that a lossless reciprocal network has a purely imaginary impedance matrix, whereas a general lossless network only needs to have a skew Hermitian impedance matrix. To conclude, the losslessness property can be expressed directly in matrix form. For a general lossless n-port network, the impedance matrix is Q Hermitian. This is the most general result and does not require reciprocity. If reciprocity is also imposed, the impedance matrix becomes purely imaginary element by element. The same conclusion applies to the admittance matrix of a reciprocal lossless network. The distinction between losslessness and reciprocity is fundamental in microwave network theory and will be useful when we later examine other network properties, including matching, reciprocity, and symmetry.